Okay, this is the very, very last section of Unit 2, and the goal here is just to relate some of the things we've already talked about. We talked about the diagonalization for A being PDP inverse, and then we'll relate this to linear transformations. So to understand the matrix factorization, A factored into PDP inverse, which, what did we call this process in 5.3? Diagonalization. As a statement about linear transformations. Okay, I'm going to tell you straight up front, this section is going to be useful in application because, as we've discussed, vector spaces don't have to necessarily be just Rn. Okay, there's a lot of other vector spaces out there. You can view polynomials as vector spaces. You can view, I could do something like I want the set of all functions that are differentiable twice on a closed interval. That is in itself, in some cases, you can prove that to be a vector space. So there's a lot of reasons why we'd want to use vector space objects. But if we want to do linear transformations now between different vector spaces, it can be sometimes difficult. What if I want to relate derivatives, say, to then just polynomials? Or what if I want to relate vectors Rn to some other object that's not just a vector in Rn? And so we're going to use coordinate systems to essentially take, irrespective of what vector space you have, we can always look at its dimension, which is just how many vectors are in its basis, to make it essentially the same thing as a subspace of Rn or whatever, how many dimensions you have. And then now I can view that entire vector space and interact with it as if it's just my good old Rn, okay? So the idea is make every single problem just a problem involving column vectors, the column vector spaces, irrespective of what those original vector spaces are to begin with, okay? It doesn't necessarily feel the most useful thing right now because at this stage of your math, you haven't done a ton of mathematics outside of the typical vector spaces. So you haven't had to interact with those things. But once you do, and once you start framing other vector spaces like on circuit boards or motherboards and those kinds of things, instead of having to deal with those objects as those objects, it's much easier to think of those objects as just column vectors, transformed with their b coordinates or whatever basis you have. So let's do a little exploration. Let V be n-dimensional, and W be m-dimensional. As means of review for your exam on Friday. What does it mean to have a vector space having n dimensions? What information does this give me about the basis of this vector space? We want to be careful about the word entries here, because that's not technically correct. N vectors. We require n vectors to form a basis of the vector space V. And so how many vectors do we require to get a basis of W? We need m. Okay. Now let's say also that T is a linear transformation. A linear transformation from V to W. Okay. Now this isn't going immediately. We get very used to thinking about this situation where V is just Rn and W is Rm. And in that specific case, we just are able to say T from Rn to Rm. And that tells us that the matrix A is an m by n matrix. So all of that is reviewed. Now what we're doing is we're stepping away from just the vector spaces having to be Rn and Rm. Now it's just any vector space that is n-dimensional and any vector space that is m-dimensional. So that's why I'm not necessarily explicitly saying T from V to W in this case, because I don't want to conflate those as the same. So we're going to we'll have two bases, right? So B will be the basis for V and W, or for V. So we'll do B and C be bases for V and W, respectively. Okay, what does this tell us? Well, this tells me that if I just take any vector in my vector space V, and I want to represent this vector, again, does does V necessarily have to be our familiar Rn? Does this vector space, are we requiring it to necessarily just be our standard Rn? No, it could be anything. This could be the vector space of polynomials, like all, say, quadratics. Okay? So this vector x, instead of just being a column vector, is itself some quadratic. And we consider that quadratic a vector because it is a member of the set of quadratics. And so what I'm going to do is I can choose a basis. In this case, the most standard one would just be I take 1 and t squared, 1t and t squared. And I can represent this vector using coordinates from the basis. And the main thing about doing these coordinate systems is that we can now represent any type of vector using column vectors in Rn. So this is now in Rn. So even though we don't necessarily start with something in Rn, the way we can treat it as if it's behaving like Rn is to just represent it using its B coordinates. So we're looking at coordinates instead of just the vector itself. And now it's going to behave nicely, so we can do all of our stuff. In a similar way, we can do the same thing for our W. So if I have some vector in my W vector space, what do you think I can say about the C coordinates, right? I can say, let me take my vector and represent it with C coordinates, and this is going to just be what type of a vector? Rn. Now, how do I know that I can conclude that? Well, how many dimensions does this general vector space have? N. Okay, again, so what does that tell me about the basis? Yeah, we need n vectors in this basis. Okay, so that means how many objects can I expect to find in script to be here? N. Okay, so then if I use how many coordinates? Obviously, we would need n entries then to store n coordinates. Okay. W has how many dimensions? M. Okay, so that tells me what about the basis C? How many vectors are in the set C? M. So then if I'm going to represent this vector using the C coordinates, how many entries do I need to store all m of those coordinates? M. Okay, so that's the correspondence here. We can always take any general vector space through coordinates to be the same thing and Rn. So visually, say this is just a general vector space V, and I have my vector x in here. What I'm doing with the linear transformation, say here's another vector space W, I can transform using my linear transformation. Now this is the image of the vector x by t, so t of x. And then independently, I can look at both of these in their coordinate systems, right? So if x is in an n-dimensional vector space, then if I wanted to represent it, say it was 3-dimensional. So I'll put up here, suppose, for the sake of example, that V is three-dimensional. And let's suppose that W, let's do a different one, is two-dimensional. Okay, so here's 3 dimensions. And then it will be, I could represent it with some coordinates. So in R3 now, where this is x1, x2, and x3, I can think of my vector x with respect to basis B as then being some linear combination of those basis vectors within the 3-dimensional framework here in R3. Yeah?
So, I don't know if I'm going to say this right, but are you basically saying if we, like, this is a very niche example, but if we needed to, like, find a way to represent through linear matrix volume to surface area, you're basically saying that with this lecture, we'll be able to find the basis to turn the coordinates that we prescribe to the volume to surface area.
Yeah, because if I think about, if I want to have a vector space, and in this vector space I have objects of volume, and then over here in this vector space I have objects of area, surface area, whatever you want to make it. So long as you can define a linear transformation between those two things, then yes, you can do coordinate representations.
And does V need to always be bigger than W? Or
those are just arbitrary numbers I threw up there. Because I can't draw a 5-dimensional graph for you, unfortunately. Yeah. So that's why I'm sticking with the 3s and 2s and 1s. I'll do another example of this in a second so that we can see what's going on. So this is going, I can think of it like that. And then over here, if this is 2 dimensions, then I have 2 basis vectors. And then the t of x now, if I want to think about it inside of R2, so this overall is R3, and this overall is R2. And this is now what happens if I take t of x as a vector, but writing with c coordinates. Okay? So why do we care about this? Well, say I had a polynomial. Let's do quadratic. So P2. And this is going to be our set of polynomials. Then I have some polynomial vector, say P of t is equal to 4 minus 7t squared. Okay? Now, does that look like a column vector? Absolutely not. This looks like a polynomial. This is very algebraic. And if I wanted to then think about this as a column vector, I can think of a basis. So what's a basis I could have for my quadratics? Well, I could define a standard polynomial basis here where I just have the vectors 1, t, and t squared. Because I know that any linear combination of 1, t, and t squared will spit out all the possible quadratics. So essentially, these vectors span P2. Now, we've been thinking of span in terms of column vectors for so long that it might be easy. You might be subconsciously associating span only with column vectors. You don't have to do that. These themselves are vectors. They just don't look like column vectors, but they are. And if I take the span, in other words, all linear combinations of these, yeah, that's precisely what I mean. It's going to be the span for this vector space. So then, if this is my basis B, I can assign coordinates to this vector P based off of these basis vectors, okay? So now I can think of the coordinates from the basis B as what? Well, how many times do I need to scale up this vector? 4. So I have a coordinate of 4 for that first basis vector. How many times do I need to scale up t? Yeah, there's none. So I don't at all. I just leave it at 0. And how much do I need to scale this vector t squared? Negative 7. That is, I have now stored the polynomial in a column vector in R3. Because P2, how many dimensions does P2 have? 3. How did I know that it's 3-dimensional? Because there's 3 basis vectors. So it should not be a surprise that this is a member of R3. So you can think of, that's one of infinitely many possible cases where this V could be this P2. And so this vector, if I want to then make a linear transformation of it over here, I can think of that separately as V coordinates over here versus transforming it into something else. Okay? Now let's say I change the basis. So now I have some other basis, C, 4 minus t and 6t squared. Is this still a basis for my P2? Yeah, because they're all linearly independent from each other. And this will span all of the possible quadratics. But now, are their coordinates going to be the same as the standard coordinates? No. So I would have to then do P of t according to the C. Notice the difference here. So these are the P coordinates, now we're getting the C coordinates. What are the C coordinates now? Why is the first one switched to 1? Yeah, because it's already at 4. So I scale this only by 1 in order to get to 4. What about minus t? Still doesn't matter, right? It's going to be 0. And then what about this one?
6 over negative 7.
Yeah. So I want to end up with 7, so or minus 7. So I have minus 7 over 6 to cancel with that. Okay? Are these coordinates the same? Wait, hold on a second. Are these coordinates the same?
No.
They're not the same. Do they reference the same object in the vector space? Yes. So what changed?
The basis.
The basis. Okay? The basis that we're doing is affecting the coordinates we use, but what I'm trying to show you with this example is that just because we change the perspective of basis does not mean we are now changing the object we're referring to. Okay? The object we're referring to is still that object. And I can then choose a perspective from which I'm viewing it in R3 in this case because it's 3-dimensional. So generally speaking, say instead of choosing P2, I just choose some other vector space. Say I want the vector space of all continuous closed functions on the interval from 0 to 1. Okay? Every possible function that is continuous closed from 0 to 1. Then I would find some sort of basis. And then depending on how many vectors I need to describe that, to span that, that's going to tell me the dimension. And so then I can just pick coordinates, and they're always going to be these column vectors with respect to how many dimensions I have. So that's what this is visualizing in full generality. And this is a step down in abstraction.
So how is C in R2 right now? We still have 3 dimensions.
Oh, this isn't analogous to the R2 situation. I'm just doing, yeah. If you were to switch out a basis, so I'm showing like the flexibility of coordinate system, so that the coordinates themselves can actually differ to refer to the same object, depending on which basis perspective you've chosen. Also, the function of this exercise is to get you familiarized with why the notation matters and why you have to specify which base you're taking the coordinates from.
How would you write in the correct way, like integration and derivative? Like if you were like to say, I want to know the derivative of like 6t squared, or like the derivative where p of t and the basis is the integral somehow or whatever. How would you write that?
That's a good question. So what I can do, let's actually look at the power rule. In general, we know is equal to what? Okay. What we can think of this as what I've done is I've taken the vector t to the n, and I have transformed my vector t to the n to the vector n t to the n minus 1. This is a linear transformation. How do I know that this is a linear transformation? Well, remember what those properties were for being linear transformation? We need that t of u plus v is equal to what?
TU plus TV.
And we also required, what was the other property?
C, yeah.
Is equal to what?
Equals CDU.
Okay, so if these are the properties we require for some sort of linear transformation, let's view differentiation as a linear transformation. Is the derivative of d dt of some f of t plus g of t, what is that equal to?
Derivative by t ft plus
Yeah.
derivative of t.
That's the same thing as d dt of f of t plus d dt of g of t. Okay. What if I do put inside of my transformation c times f of t? So where the functions are the vectors now.
C times the derivative by t, whatever.
I don't know about you. The notation's a little bit different, but that sure looks and behaves exactly like a linear transformation. Okay? So that's kind of that's why when we talk about this t, it's no longer going to be just some sort of t of x or t of something, like we used to have with our standard Rn to Rm. Now, we could literally have a transformation be some sort of rule as in differentiation, okay?
Would it work for, like, I don't know if this is still might be done, but like natural log, like how to do the derivatives by natural log or inversion by natural log and stuff like that?
Well, you can show... I'll answer your question like this. Is the natural log of a plus b equal to the natural log of a plus the natural log of b?
No.
No.
So therefore no.
Okay, so what property does that inherently fail as a transformation?
The first one.
T
The first one.
equals-
So if by definition the transformation requires this, can that definitionally be a linear transformation?
No.
No. So you can check this with a lot of things.
That's true.
Yeah.
So why the polynomial one works is because we don't really see it as like, actually, what I'm really saying is because we're only adding like constants to one t squared, and t cubed is not like.
Right, yeah, we're just scaling basis
We're
vectors.
scaling it.
Yeah.
So because it's a scalar, we can do it.
Mhm.
While if it isn't a scalar, we can't.
Right, you're not multiplying your basis vectors by vectors themselves across all the
So
things.
you can't do product form.
Now, here's kind of what's fun with the derivatives. Let's take the vector space P n, okay? So this is going to be all of the possible n degree polynomials. So we'll start with some a naught plus a1t plus a2t squared, so on and so forth until I get to my a n t to the n. And that's going to be true. We need these scalars to just be in R. Okay? So this is Pn. And now I can look at Pn minus 1 is going to be very similar, right? A naught plus a1t plus a2t squared plus until I get to a sub n minus 1 t n minus 1 for a naught to a n minus 1 in R. Yeah? Okay, so let's think about this. In general, I have a transformation. We call it differentiation. d dt, let's define a vector actually. So let's define a general vector. Let's call this vector P. It doesn't really matter what you call it, whatever you want. P of t, in general, if P of t is in Pn, then that tells me something about the vector P. That means I can express P of t with some constants C naught plus C1t plus C2t squared all the way down to Cn t to the n, right? Where I have scalars C naught to Cn. Do we all agree? We all agree that if I choose to put a polynomial in here, what that means is I am just doing a polynomial of degree n. Okay, so now if I actually enact this linear transformation, right? So if the transformation is defined by this, then d dt of my vector p of t is going to be the same thing as transforming c naught plus c1t plus c2t squared plus 2cn t to the n. Yes?
Yeah, but you need to just expand it.
And I know that this is going to be equal to what?
The dt c naught plus dt c1t.
Right, but we know what these are, right? We can just do the brutal. So what's the derivative of a constant?
0.
What's the derivative of that?
C1.
What's the derivative of this?
2C2.
What would the next one be?
Dot 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 dot.
Like 3 c3t squared, and then so on and so forth until we get to what? What's the general term look like? NCN t to the n minus 1. Okay, so here's now what we can do over here.
Sky, you must have
Am I missing a t?
2C2T.
Thank you.
and for
Okay, so now let's do this in terms of our linear algebra stuff. Okay, I have a vector space Let's take stock of what we have. We have two vector spaces. What are my two vector spaces?
P of t and then the transformation.
Yeah, Pn and Pn minus 1. Okay, how many dimensions does Pn have? Tempting, isn't it?
+1.
Yeah. So this is n plus 1 dimensional. And this one has how many dimensions? N dimensions for that. N dimensions. Okay. Let's now think. Do we have a linear transformation?
Yeah.
Let's call the linear transformation of differentiation t. Okay? So t is going to be relating a linear transformation given by the derivative, basically. d dt of a polynomial. Well, I have to actually state the polynomial for the rule. But effectively, like if I have Tn and t minus 1, okay? So, let's take a look at what we've got. I have some vector p. This vector p is a member of which vector space? Yeah, the first one, okay? This one is a member of the first vector space. Now, by itself as a polynomial, that's not the most helpful thing if I want to think about my linear matrix algebra stuff. So if I represent this now using a column vector, I can then say that, well, we need to find bases, so that's what we're missing. So what bases do you want to use for these vector spaces? Well, let's use the standard bases. So a basis for Pn is going to be 1 t squared, and where do I stop? Tn. And then my second basis for my Pn minus 1 is going to be 1 t squared. Where do I stop this time? So that's how we know the dimensions, because we can count how many vectors are in each of those. So now we have bases, we have vector spaces. That means you can represent these with coordinates. So P being a member of the first vector space, Pn, tells us, especially in light of the basis B, that if I take the B coordinates, what is that going to be now?
A1, A0, A1, A2.
Close, yeah.
all the
We've
way
already
down.
defined it here, so let's use the values that we defined.
C1, C2,
Yeah.
Cn.
So we have C0, C1, C2. Interesting. It's just coefficients. Okay, so I kind of march down. Alrighty, what happens to then? This is going to be notationally kind of goofy, but I'm going to use this to tie back to what we previously did. If I take the transformation, the linear transformation of the vector, right, where we understand that the linear transformation is this transformation of differentiation, my power rule, then that is this vector. So if I want to represent, there's a lot of brackets here, but stick with me. The brackets on the outside are indicating that what I'm capturing on the inside is in the C coordinates. So this transformed vector P of t through the differentiation linear transformation, now represented with coordinates given by the basis C, is equal to, what are those coordinates?
One,
C1,
two, three, to n.
Well, we don't forget something really important, right?
Oh,
What is the, yeah, so we shift everything over. So make sure you start with the scaling with C1 instead of the C0, okay? And then we have 2, C2, 3, C3. And that's going to go all the way down to what?
Cn.
Scott?
Yeah?
Why is C1 in there still if the P of t has the the C not already in it?
Well, this gets transformed to 0.
Oh.
And then we have C1 becoming the next.
Because
Yeah.
the transformation of PT is the derivative.
Yes. So I'm trying to get you to see how this notation I'm using to very specifically suggest the notation that was drawn on the board and was here just a minute ago. Okay? To tie those things together. This is just something concrete that you can put your hands on, actually. Okay. Kind of interesting. So we want the how many entries? So this is in R what? And this is in. So what I could say is that we have a transformation, a linear transformation between vector spaces that is effectively the same thing as taking Rn plus 1 to Rn. So to answer the question, can I collapse the dimension of my vector space through a transformation? You in fact can. You collapse that every single time you do a power rule.
So could you do another side topic? Can you do, so how hard would it be just to so if you need, like the example of needing to do volume to surface area, you need to use a very specific example because you can't just say, this line is sphere.
Yeah, I can't just fabricate some. That's unfortunately not something I can do. Okay.
The surface area of a hyperbolic, right?
Does this make sense?
That'd be real. So, another question. How much of this covered the lecture that we just spent?
Well, I guess you'll never know. But the okay, here's the main takeaway. The reason why I like showing this actually is because when I was taking linear algebra myself back in my freshman year, I remember seeing this example and realizing who could have thought, that the math class about lines and systems of linear equations has the language effectively to describe calculus.
Let's go.
Okay? That's kind of crazy.
So now we
Some of these things that we don't think are related to linear systems, or that we don't think are related to these kind of fundamental properties, end up just being kind of, it's like the Scooby-Doo, you take the mask off and it's yourself. It's like, it's been there all this time, and you just weren't aware of it or prepared to know that that was what was going on. How many of you have already taken differential equations? How many of you are taking it right now? Then when you start talking about homogeneous systems, so odd and so strange that suddenly we have these linear combinations of functions all set equal to specifically 0. I wonder where that concept came into play. I wonder where that concept of, if I really started looking back at my differential equations homework and these, especially I think it's the undetermined coefficients, and when you have systems of these equations, if you have a basis and define some sort of basis that is reflective of the overall vector space that you're handling, then you can start thinking of coordinates for those functions, and the behavior is going to be exactly the same. So that's why a lot of the terminology bleeds between the two classes, like homogeneous, like linearly independent function sets, like those kinds of things, is because it's all the same. It just chooses depending on which window you're looking at it from.
and last question, hopefully, is how would you do it backwards, like integration, if you want power?
Well, to perform anti-differentiation, you could show through the properties that anti-differentiation does in fact satisfy the properties to be a linear transformation as well. So I would maybe consider that an inverse, because you would need to, inverses have very specific properties, but it definitely is a linear transformation. Okay, that was a lovely side tangent.
Now back to the regular.
Okay. So the way we'll finish today is we'll answer this question. How are the vectors x given with b coordinates and the transformed vector given with the c coordinates related? So given the basis vector, so say I know that my basis b is b1 through bn. And we have some vector x where we can use r1, b1. So these are just the coordinates of x in basis b, with scalars, of course, ri. Then I can express the b coordinates by design as r1 through rn. Yes? So by making this explicit linear combination, I'm basically just saying, hey, I want to use r1 through rn as coordinates in the basis b. Okay, another thing that we'll also have, notice this. If I take now the transformation of the vector x, t of x is equal to t of r1, b1 down to rn, bn, which, because this is linear and the superposition principle gives us r1 t of b1 down to rn t of bn. Now let's take the c coordinates. So I'm going to put this into c coordinates. And the scalars are just hanging out on the outside. So r1, and then I'm going to take my t of b1 in c coordinates all the way down to rn, and then take my transformed bn basis vector and take that in c coordinates. If I do that, you might recognize that this vector equation is very, very familiar to like 1.4 of this class, is I can now make a matrix with all of these vectors being the columns of it, right? So I can do t of b1 in c coordinates all the way down as a column, and the last column is going to be transforming my nth basis vector and then taking the transformation in c coordinates. And I'm multiplying this by r1 through rn. Going between this is these. If you replace this entire chunk with just a singular variable like a1, it'll look exactly the same as like how we had the columns of the matrix A. These are just massively disgusting chunky versions of how to write a column vector of the matrix. Okay. But r1 down to rn is what? It's just the b coordinates. So I don't need to put this representation like that. I can just say, oh, let me take my original vector x, but expressed with its b coordinates. And then if we take this entire horrendous thing and call this m, where that m is definitionally what we call, or m is called the matrix for t relative to the bases B and C. Because what's this doing? Is it saying this should look a lot like how we did the change of coordinate section 4.7 lecture? This matrix is something you've already seen before, but just in a higher generality, okay? We've already had this idea of using a matrix to transform my basis vectors, and that multiplied by something in the b coordinates spits out a new coordinates for c. We're doing the same thing, and we're just simply saying that if it's a linear transformation, you can do the same thing for the transformed basis vectors and the resulting transformed vector. So I could say that the vector, the transformed vector x, given with c coordinates, is the same exact thing as taking my matrix that's related to the bases, which is really just the columns of transforming each individual basis vector, and then taking that transformed basis vector and representing that with c coordinates times the original vector itself given in its b coordinates. So when you do a change of bases, so this goes back to 4.7. So recall 4.7. When you're changing the coordinate system, are you changing the entire vector space, or are you just staying in the same vector space? If I'm switching the coordinates out, does that necessitate I change the entire vector space? No. So what I'm doing is I have this same vector space. I'm going from V to V. I'm not changing that. But what I am doing is I'm changing the basis perspective. So when I think about what's happening here, if I'm just going from V to V, I'm really just performing a linear transformation of t of x is equal to x for all of the x's in my vector space. If I'm changing the coordinates, I'm not trying to change the vectors themselves. I want the vectors to remain the same. I just want the coordinates that I used to describe it to change. So this is the identity. So if you think about that, let's construct our M. What does M have to look like? Well, M is going to have these columns, T of B1. If T of B1, plug B1 into here, what gets spit out? Okay, so say x is equal to the basis vector B1. Then it'll just be what? B1. So then I just have B1 represented with C coordinates. That's going to go all the way down to Bn given C coordinates. But this is literally what we meant by the change of coordinates matrix, right?
Right.
That in itself is what we meant when we were constructing our P taking B coordinates to C.
Yes.
So really all this is doing is it's just broadening that perspective to general linear transformations. Okay, so there's a reason why that equation should look so similar to this equation. X with C equal to my change of coordinates matrix from B. This, if it's just identity, then T of x is always x. If it's just identity, then the M is just going to be my change of coordinates matrix. And then I have my basis B. Okay? Does that make sense? Questions, comments, concerns? Okay. Some things to do for before you get to Wednesday. When we come to Wednesday, I'm going to just come up with some problems that will reflect skills that you will need to know. They aren't going to be actually related per se to the questions on the exam, but they will be specifically designed so that if you can't solve the questions on Wednesday, then that's a very good thermometer check for where you are at for Friday. Okay? So before Wednesday, please, please, please review vocabulary. What I don't want to have to do is ask you, what is rank? And all of you look at me like this. Because you know what I might do? I might then say, you know what? I'm not going to do this review. Y'all can figure it out. And then we don't do a review. Okay? Because the function of review is for you to take a test. It is not for me to take the test. Okay? Question.
So are the questions going to be similarly styled to how the exam's going to be, or is it going to just be fundamentally similar?
It'll be like, the only way you're understanding this question is if you really understand the definition and concept. And if you really understand that definition and concept, it will translate perfectly. Yeah. Because that's really what it comes down to.
So you're not, like last exam, are you gonna ask us, like, you know, what's it called?
Oh, I'm not going to bother you with handwriting out all the definitions
Okay.
again. Yeah. That was just kind of like a, hey, definitions matter, but now you don't get free points for that anymore. Because that's like a fake math question. That's not a real math question.
Well,
Because
same
last
kind of
exam, I think I focused too much on
this
grammar.
Okay, yeah, so no, don't do that. But if you don't, here's the thing, if you don't know the definitions, there's just a solid, like, 100% of the questions you won't be able to solve.
Yeah.
Okay, so take that with a grain of salt. Okay. Make sense? Alrighty, I will see you guys on Wednesday. And if you're on the field trip, that's okay. Everything will be recorded.